Hello everyone. Today I am covering the distributed minimum spanning tree topic. My name is Rahul Zadav, roll number 274, division B. Spanning tree. A spanning tree can be defined as a subgraph of undirected connected graph. It includes all the vertices along with the least possible number of edges. If any vertices is missed, then it is not a spanning tree. A spanning tree is a subset of graph that does not have any cycle, and it is also cannot be a disconnected. Here, first we see the graph. Graph can be defined as the group of vertices and edges to connect these vertices. And there are following three types of graphs: undirected graphs, connected graphs, and directed graphs. Undirected graphs. An undirected graph is a graph in which all the edges do not point to any particular direction. They are not undirectional. They are bidirectional, and it also be defined as a graph with a set of v vertices and set of e edges, and each edge connecting two different vertices. Second one is the connected graph. A connected graph is a graph in which the path always exists from vertex to any other vertex. A graph is connected if we can reach any vertex from any other vertex by following edges in either direction. And third one is a directed graph. A directed graph are also known as a digraphs. A graph is a directed graph if all the edges present between any vertex or nodes of the graph are directed or having a defined directions. Example of a spanning tree. A spanning tree, here we can see the weighted graph. There are four vertices and four edges, which will be denoted as vertices as A, B, C, D. And we can see there the weighted graph has given the cost between A to B is 5, A to C is 6, C to D is 3, and B to D is 2. And every spanning tree containing total number of 2 raised to n minus 2 spanning trees means if I want to find the how many spanning tree can be created from this, then I will use 2 raised to n minus 2, which means n is n raised to n minus 2. N is nothing but the vertices of the spanning tree. Here total 4 vertices, so formula will be 4 is to the power 4 minus 2, means 4 is to 2 is 16. The total number of the spanning tree can be created from this is 16. Like that, we can use the this formula. The application of the spanning tree are civil network planning, computer network routing protocols, and cluster analysis. And here, a complete undirected graph can have, just before I told you regarding this n raised to the power n minus 2 number of spanning tree, which has the n is the number of the vertices in the graph. Here, we can see this example. There are A, B, C, D vertices, and if we consider the minimum spanning tree from A to B is 5, cost A to C is 6, and C to D. Then total cost of minimum spanning tree is 5 plus 6 plus 3 is around 40. Like that, from second, we have remove the edge from A to B, and we consider A to C, C to D, and D to B. The cost is 6 plus 3 plus 2 is 11. Another spanning tree containing cost of A to C, A to B, and B to D is around 13. And from A to B and B to D and D to C is around 14. There can be more than one spanning tree of a connected graph G. A spanning tree does not have any cyclic loop. Here we can see that every spanning tree have edges, but they are not in the loop. They are not in a loop. A spanning tree is a minimally connected. So removing one edge from the tree will make the graph disconnected. So every graph is disconnected from removing the one edge. A spanning tree is a maximally acyclic. So adding one edge to the tree, creating the loop. If I add B to D one edge, then it will be created the loop. Then it will be not considered as a spanning tree. The spanning tree has n minus 1 edges. So we can see that there are total 4 vertices. And then if I see the edges, then it will be n minus 1, means 4 minus 1 is 3. So there are total 1, 2, 3. Every spanning tree containing the 3 edges in this case, because there are total n is equal to 4, means 4 vertices are given in this problem statement. Minimum spanning tree means a minimum spanning tree can be defined as a spanning tree in which the sum of the weight of the edge is minimum. Here we can see that there are in this example, we see that the first case from B A to B, A to C, and C to D, their cost is 14. And in second case, cost is 11. In third case, cost is 13. And in fourth case, cost is 10. So the minimum spanning tree means the sum of the edges which has edges is the minimum, and the means cost is the minimum. Then we can see that the sum is 10, and this is the minimum cost of the spanning tree in these four conditions. So we will choose the minimums MST, minimum spanning tree is this diagram we can consider. So the minimum spanning tree that is selected from the above spanning tree from weighted graph is A to B, 5 cost, 5 to D is 2, and D to C is the 3. The total sum is 10. The weight of the spanning tree is the sum of the weight which due to the edge of the spanning tree. In the real world, the weight can be considered as the distance and the traffic load and any random value from two vertices. Next, algorithm for minimum spanning tree. There are two types of algorithms for finding the minimum spanning tree and a weighted graph using Prim's algorithm and Kruskal's algorithms. First, we will see the Prim's algorithm. Prim's algorithm to find the minimum cost spanning tree uses the greedy approach. Prim's algorithm shares similarity with the shortest path first algorithm. Here, if we see this example, there are this graph containing the vertices S, A, B, C, D, and T, and it every vertices edge will have denoted with the some randomly given as a cost, and we have to find the we have to check the minimum spanning tree using the Prim's algorithm. There are some steps which will be we will see in the next slide, which cover the how we can find the shortest means minimum spanning tree using the Prim's algorithm. First step is remove all loops and the parallel edges. Here we can see that there are two loops in our diagram. A to B, there are two paths. From A to B is a 6 cost, and A to B is from another loop is 9. So we can remove the maximum cost of that. Means A to B with the 9 cost, we can remove that. And from C to C, there is no use of this loop. It will be charging a one cost. So we will also remove that. Second step, choose any arbitrary node as a root node. In this case, we can choose any root, any node as an arbitrary node or root node. In this case, we choose a S node as the root node of the Prim's spanning tree. This node is arbitrarily chosen, so any node can be root node because if I consider T, then it will be every node, every vertex in the graph is connected with the one of the edges. So there is no issue to select randomly or select any node which is known as the arbitrary node or root node. Here we if here I choose the S as a root node, and next step, check outgoing edges and select the one with the least cost. From S, there are two edges which has the S to A edge and S to C with the cost of 7 and with the cost of 8. So the minimum cost of S to A is the 7. So we select the minimum cost in our spanning tree. So the selected means added into the result will be S to A. Next step will be from A. There are two paths which will go from A to C and A to B. Then the minimum cost of A to B and A to C is a 3. A to C, it is a 3. So we selected S to A. Then after that, A to C is the selected graph H. And then after C, we have a two path with A to C to B and C to D, which is the minimum. Then it is a 3. So we selected to C to D as the minimum edge cost. So we selected the C to D edge. After there are two edges with the similar weight from D to B and D to T. So we have to select both because we until from this path we didn't reach to the B anywhere from A to B or C to B. So we have to select, we have to consider B also. So from B to from D to B is a 2, and D to T is also 2. So we selected these two things, and this is our final spanning tree using the Prim's algorithm. And the final check out our problem. There are only one path which has the minimum cost or minimum uh, cost value from all the edges, which will considering our uh, spanning tree, which is resulting as a S to A to C, C to D, and D to B, and D to D. Next algorithm is the Kruskal's spanning tree algorithm. The Kruskal's algorithm to find the minimum cost spanning tree use the greedy approach. This algorithm treats the graph as the forest, and every node it has an individual tree. A tree connects to another only, and only if it has the least cost among all the available options and does not violated the MST properties. MST properties, minimum spanning tree properties. So yeah, we can take the same problem statement, and we will see how Kruskal's spanning tree work on this example, using the example. And there are some steps we will see. First step is remove all loops and parallel edges. The same things from A to B, there is a one loop which has the maximum cost as compared to 6. So we will remove the A to B of 9 cost and C to C with the 1 cost. Second step, arrange all edges in their increasing order of their weight. We have considered B to D. B to D has a 2 cost. We will be considered as in increasing order, and D to T has a 2 cost. Then after that, we have after these three, there are two edges from A to C and C to D. We are then considering as A to C and C to D as the 3 cost. From C to B, there is only one, and after that B to T is a 5, and then A to B as a 6, and S to A as a 7, and S to C as a 8. After that, arranging all the edges in the increasing order of the weight, we are considering the same arbitrary. We have to find out the start with the minimum, means least weightage cost, and we have to select the edge with their node. Then currently we can see that there are first two edges, B to D. B to D, we will be considering the edge cost is 2. So we have selected and will be added as into the result. After that, D to T, we until that we didn't visit to T on vertex. So we also considering this as a result, resultant value. After that, A to C, and C to D. So A to C and C to D we can be added to the our result because we didn't reach vertex A and C before. So after that, our graph will be look like this: A to C and C to D. D has to connect it with B and T. After that, we have cost of 4 and will the edge corrected from vertex C to B, but it will be create a cyclic form, and we don't have in the spanning tree we don't have to create the cyclic form and circuit. We don't have to create the circuit, so we have to ignore this case C to B, and we already visited to the B from D to B with the least cost. Then we have to we don't have to need to consider this edge also, C to B, and we will ignore this state. After that, B to T is a 5. B to T is a 5, and this also create the circuit. So we have to be ignore this case also. A to B is the 6. The cost is 6, and it will also create the circuit from A to B, B to D, D to C. So we have to we don't have to need to consider the cost of A to B with the age 6, with the 6 cost age, and we also removing during this state. Then S to A is the new vertex we are visiting first time to that S, and so from we have to consider that S to A with a cost uh, of age is 7. So before we this is the diagram, we are not considering this because of this circuit. And after that we check about 5 and 6 also, and it will be not considering. And then there are only two edges remaining from S to A, S to C, and the list is 7, so we are selecting S to A, and this is our final result of our algorithm from using the increasing order of weighted S to A with the 7 cost, A to C is a 3 cost, C to D 3 cost, D to B is a 2 cost, and D to T is a 2 cost. Thank you.